Welcome to section 4.10. All right, gentle people, what we're going to cover in this lecture is the last class of reactions, and that is going to be oxidation-reduction reactions or redox reactions. Now, an oxidation is when a substance loses an electron, and a reduction is when a substance gains an electron. You can use the mnemonic device, Leo the lion goes grr, lose electron oxidation, gain electron reduction. There's another one that people like to use, and that's oil rig. Oxidation is loss, reduction is gain. So let's go ahead and take a look at an example of this. So in this reaction right here, I have magnesium solid reacting with HCl, giving me magnesium chloride plus H2 gas. Now, to help me look at this reaction and show that this is an oxidation-reduction reaction, well, we can go ahead and look at the net ionic equation. And from here, we can really see that we have a loss of electrons and a gain of electrons. And the way you can tell that is by noticing that things change charge. So magnesium right here has no charge, and then it goes to the magnesium 2+ ion. So I can go ahead and just focus on what's happening with the magnesium, and what I will see is that if magnesium goes from the neutral to the +2, then it has to lose 2 electrons. Since it's losing 2 electrons, magnesium is oxidized. We can also see this looking at hydrogen. Hydrogen has a +1 charge here, and it is neutral on the other side. So in this case, what we'll see is that we started out with 2 hydrogen ions, we added 2 electrons, and I got the H2 molecule. So since it gained electrons, we say that H+ is reduced. Now, in redox reactions, when we balance them, what we will find is the number of electrons gained is going to equal the number of electrons lost. Now, when I look at these reactions, it's really easy to see that electrons are lost and gained because things become charged or uncharged or they change charges. However, in chemistry, this reaction here is considered an oxidation reaction. Now, what I want you guys to note, there are no ions here, so it's really hard to keep track of electrons being lost or gained. So what we need to do is we need to assign something called the oxidation states. And this is a way for us to keep electrons formally. This is a bookkeeping method that chemists have devised. Now, your book tells you how to assign oxidation states, but I like this chart right here. The most important thing that I want you to remember is that oxidation state and charge are 2 different things. However, they are related to each other. An oxidation state is a hypothetical idea. It is asking if everything was an ionic compound, what would be the charge of that ionic compound? Again, to emphasize this, CH4 is a molecular compound. But let's go to my hypothetical world and say, if this was an ionic compound, how would I put the charges on hydrogen and carbon? And so that is the game that oxidation state is playing. It is the what if game. So on this sheet, what you will see is rules to help you assign oxidation state. Now, the first thing I want you to understand with this is that the rules are listed in priority, meaning that this rule takes precedence over rule number 2, and I'm going to follow rule number 2 before I follow rule number 3. So if 2 rules are in conflict with each other, always go with the rule that is on top on this list. So let's go ahead through some basics of this rule. The first rule says that the sum of the oxidation states equals the total charge of that compound. So an easier way to say this is saying that if something is charged, then that is going to be its oxidation state. So for example, in that last example, what I had magnesium. So if I have magnesium and it's neutral, the oxidation state is 0. If I have magnesium 2 plus, well, then the oxidation is plus 2. The hydrogen we saw there had a charge of plus 1, and so that means that its oxidation state is plus 1. The next rule, rule number 2, is things in their elemental form have an oxidation state of 0. Now you can see magnesium was in its elemental form, and what you'll see that it has an oxidation state of 0. Also, what you'll notice is H2. This is the elemental form of hydrogen. This has an oxidation state of 0, meaning each hydrogen has an oxidation state of 0. So when you assign oxidation states, you're assigning it per atom. So the next rule, any atom in group 1 is going to have a plus 1 oxidation state. And this should make sense to you. If I look at the first column in the periodic table, when these combine with things, well, they're going to go to the plus 1 charge. And again, charge equals oxidation state. So for example, sodium in any compound, well, it's going to have an oxidation state of plus 1. Now, the same is going to happen for group 2. And so this is the second column in the periodic table. All of these adopt a 2 plus charge. And if they adopt that charge, that means they are going to have a plus 2 oxidation state. So let's talk about hydrogen. When hydrogen is combined with nonmetals, it's going to have a plus 1 oxidation state. If it is combined with metals, it's going to have a minus 1 oxidation state. So to give you an example, lithium hydride in your lithium hydride batteries. Well, the lithium is a metal, and then hydrogen is connected to a metal, so in this case, the oxidation state of hydrogen is minus 1. If I were to have a molecule like CH4, well, carbon is a nonmetal, and so that means the hydrogen's oxidation state in here is going to be plus 1. Fluorine is always going to have negative 1 as its oxidation state, and then oxygen has a whole bunch of rules. What you will see is that oxygen 90% of the time is going to have an oxidation state of minus 2. It's only when it's combined with certain things where it will change its oxidation state. And those certain things are usually going to be something that already has a rule associated with it. Let's take a look at an example. Let's look at KO2. Now, the first thing we're going to do is assign the oxidation state of potassium. And that's because potassium has a rule associated with it. It is in group 1, the first column of my periodic table, so it has an oxidation state of plus 1. Now, I know based on my first rule that all the oxidation states have to equal to 0 because the charge of this molecule is 0. So in this case, what I know is that this O2 has to make up this minus 1. And the only way that occurs is that if each one of the oxygens is minus 1/2 in oxidation state. And so this is what that oxygen is acting like. It is acting like a superoxide where the oxidation state is minus 1/2. Again, to remind you, there are 2 oxygens in here to make up that full minus charge. That's why each of these are minus 1/2. And finally, the last rule here is that halogens are going to be in minus 1 unless a rule above is going to take precedence. And that you have to worry about are oxygen, fluorine, and also this last clause right here. So let's first talk about oxygen, and then I'll talk about the last clause. So for example, if I have the compound OCl2. So the first thing I'm going to do is I'm going to look at the rules for oxygen. Now again, oxygen can be variable, but what I'll notice is all the rules above it are not forcing oxygen into anything. So if oxygen is not forced into anything, then it's going to be minus 2. So remember again, I have to sum up all the oxidation states, and this has to equal 0 because my compound is neutral. So that means those two chlorines have to be +2, and so that means each chlorine is +1 in oxidation state. So let's talk about that last clause, the more electronegative halogens. So if you look on the periodic table, what you will see is that fluorine, chlorine, bromine, and iodine make up the halogen. As you go up this row, the more electronegative you will be. So what this rule is saying is that if you have ClBr, and this is the molecule you are looking at, if I look at the rules, what I'm going to say is that chlorine, because it is higher up on the periodic table, it is more electronegative, it gets to be -1. Now, because this is a neutral complex, this has to have all its oxidation states equal to 0, so that means bromine is going to be +1. All right, let's go ahead and do some practice out with this. So I'm going to first prove to you guys that this is a redox reaction. So the first thing I'm going to do is assign oxidation states. So I want you to pull up that chart because we're going to assign the oxidation states to everything. So what I'm going to do is I'm going to have two rows, oxidation states, and to help me on the bottom is I'm going to put the sum of all the oxidation states. So let's look at our first compound. So first thing we have is carbon. There is no rule for carbon, so carbon can be variable. Now there is a rule for hydrogen. The rule for hydrogen is it's going to be +1 with nonmetals. So I have +1 oxidation state for hydrogen. Since there are 4 of them, I can sum up all their oxidation states to be +4. Now, the reason I'm doing this is I want to figure out what carbon is. But I know that the total charge of this has to be the sum of my oxidation states. And so the total charge on this molecule, CH4, is 0. So that must mean X equals -4. So carbon here is in an oxidation state of -4. Now I have oxygen. It's in its elemental form. So that means its oxidation state is 0. Let's go to my products. Let's start with carbon. Again, I don't know what it is. It is a variable oxidation state. There is no rule. Now, oxygen has a whole bunch of rules, but since carbon isn't forcing it to do anything, its oxidation state is -2. There are 2 oxygens, so in total, it's contributing -4, and carbon dioxide is neutral. So in this case, X equals +4. So the oxidation state of carbon is +4 in here. Lastly, let's do water. So hydrogen has a rule. It's going to be +1. There are 2 of them. And so oxygen has a whole bunch of rules, but since it's connected to hydrogen, which has a rule that is higher than oxygen, it is being forced into something. So we have to figure out what it's being forced into. So I know water is neutral, so now we can just solve for X, and in this case, X is -2. So this is the oxidation state for oxygen. Now right here, these are the oxidation states for every element in my reaction. Now what you will see is that carbon starts as -4 and then goes to +4. Oxygen starts at 0 and then it goes to -2. Hydrogen started at +1 and ended up in the same oxidation state of +1. So if things are changing oxidation states, that means a redox has occurred. We can see oxygen went from 0 to -2, so it reduced in oxidation number. So it is reduced. Carbon went from -4 to +4. Since its oxidation increased, it is oxidized. So let's go ahead and practice a few of these. So go ahead and tell me what is the oxidation number of chromium in this compound. All right, gentle people, let's go ahead and write our formula down. And I'm going to go ahead and use that two-row method. So I'm going to have the oxidation states on top. And so this is what I'm going to report as the oxidation state. And for bookkeeping purposes, I'm just going to sum them up to help me out. So the first thing we see is that we have sodium. Now, sodium is in group 1. It has a rule. Its rule is +1. And so we are going to say that we have 2 sodiums. So the total contribution of all my sodiums is going to be +2. Now, chromium is something that is variable. There is no rule for chromium, but I know that there are 2 chromiums in here. Lastly, oxygen has a bunch of rules. Now, it is not being forced into anything, and that's because chromium is the more variable atom here. And so if oxygen isn't being forced into anything, it becomes -2. And so there are 7 of them, so this is going to be -14. And if I sum all this up, this has to equal the charge of this complex, which is 0. So if I go ahead and solve for x, in this case, x is going to be +6. So that is going to be the oxidation state of chromium. All right, let's go ahead and try a few more of these out. Is the following a redox reaction? Okay, let's go ahead and take this apart. So my first complex is an ionic compound. It is made out of Cu2+ and OH-. And so remember, charge is going to equal oxidation state. So the oxidation state of copper here is going to be +2. So the next thing is we can just go ahead and look at OH- by itself. So again, let's go ahead and use our 2-row analysis. We have hydrogen, which is +1 because it's connected to a nonmetal. Oxygen is going to be variable. And so what I have is 1 oxygen +1 equals -1 because each of my hydroxides are charged as -1. If I solve for x, x here is -2. So +1 for hydrogen, -2 for oxygen. So let's go ahead and look at the other side. Again, we have an ionic compound. It is made out of the copper 2+ ions and oxide, which is 2-. So here we have +2, -2, because oxidation state equals charge. And you guys can see one of the first examples that I did was water. And I told you guys, and you can look on that slide again, that hydrogen is +1 and oxygen was -2. So if we look at all of this, what we'll see is copper goes from +2 to +2. So it's not changing oxidation states. Oxygen is going from -2 to -2. It's not changing oxidation states. And hydrogen +1 to +1. So nothing here changed oxidation states, which means that this is not a redox reaction. I have to have something change oxidation states for it to be a redox reaction. All right, let's go ahead and do this last question here. Okay, so let's do our 2-row analysis. We have our oxidation state and summing up just to keep my books in order. So phosphorus does not have a rule associated with it. Chlorine is a halogen. It is not being forced to anything weird, so it is going to be -1. So -3x, this all equals 0. So in this case, x equals +3. So in this case, my phosphorus is going to be +3. My chlorine is -1. Cl2, well, this is chlorine in its elemental form, so 0 for its oxidation state. Lastly, we're going to do the same thing. Phosphorus is variable. Chlorine's not being forced to anything. -5x. All of this equals 0. So X equals plus 5. So I can go ahead and say that the phosphorus on this side is in the plus 5 oxidation state. So now what we can see is that we are changing oxidation state. Phosphorus went from plus 3 to plus 5. It increased in oxidation state. It is being oxidized. 2 of my chlorines were at 0, and they all went to -1. So these 2 chlorines became -1. It reduced in oxidation state, so it is being reduced. So this is a redox reaction because phosphorus is being oxidized, chlorine is being reduced. Well, Chem 1A, I hope that made sense, and remember to stay safe.